Hello my dear students, welcome to my electrochemistry class. In today's video, let's learn about the most interesting and important part of electrochemistry, that is the derivation of Nernst equation. And we can also discuss its applications. In the end of the video, we can also look into solving some problems in connection with Nernst equation. Nernst was a German chemist known for his work in thermodynamics, physical chemistry, electrochemistry, and solid-state physics. His formulation of the Nernst heat theorem paved the way for the third law of thermodynamics, for which he won the Nobel Prize in Chemistry in the year 1920. So, Nernst derived an equation which is relating the EMF of an electrode or cell with the equilibrium constant. So if they are asking you to define Nernst equation, we can say that it is a simple relation between EMF and equilibrium constant. Equilibrium constant is the ratio of the concentration of the products to the concentration of the reactants. So accordingly, the equation can be rewritten as E is equal to E0 minus RT by NF ln concentration of the products upon concentration of the reactants. To derive this equation, let us consider the following redox reaction occurring in an electrode. So Mn plus N electrons, reversible arrow, gives M. This is the redox reaction. For this equilibrium, the free energy change delta G and the equilibrium constant K are given by Van 't Hoff's reaction isotherm as minus delta G is equal to minus delta G0 minus RT ln concentration of products upon concentration of reactants. Here, delta G0 is the standard free energy change. The decrease in free energy minus delta G will produce electrical energy. As per the equation 1, we notice here that the reaction involves n number of electrons. Therefore, n Faraday of electricity is obtained. If E is the EMF of the electrode and the total electrical energy will be NFE joules. Minus delta G is equal to NFE joules. Similarly, minus delta G0 is equal to NFE0 joules. Here, E0 is the standard electrode potential, which means it is the EMF which is obtained in standard conditions like standard temperature of 25 degrees Celsius or 298 Kelvin and standard 1 atmospheric pressure. This equation 2 then will become, by replacing the values of delta G as minus delta G is NFE and minus delta G0 is NFE0. By replacing the values of these two, the equation 2 will become NFE is equal to NFE0 minus RT ln concentration of M by concentration of Mn plus joules. Actually, the concentration of M, it is a pure solid metal. So for any pure solid metal, the activity of the metal will be 1. So by replacing this value of M as 1, the equation becomes like this. NFE is equal to NFE0 minus RT ln 1 by concentration of Mn plus joules. Now when that Mn plus in the, that is 1 by Mn plus is log 1 minus ln Mn plus. So this will be rewritten in this mode. NFE is equal to NfE0 plus RT ln Mn plus concentration. Now divide this whole equation by Nf. When we divide, we get E is equal to E0 plus RT by Nf ln concentration of Mn plus. When the natural logarithm is converted to logarithm to the base 10, we have to multiply by 2.303. So the equation becomes E is equal to E0 plus 2.303 RT by Nf log concentration of Mn plus volt. Now R is nothing but it's a gas constant, T is the temperature, N is the number of electrons that is involved in the reaction, F is the Faraday of electricity. Now this R, T and F is the same for all reactions because gas constant R is having the value 8.314 joules per Kelvin per mole and F is the Faraday which is 96,500 coulombs, T temperature which is when it is taking place in standard conditions it is 25 degrees Celsius or in Kelvin scale it is 298 Kelvin. So when we replace the values of these items like R, T and F, we get the value as 0.0591 volt at standard condition, that is at 25 degree Celsius. So that 2.303 RT by F can be replaced by this value E is equal to E0 plus 0.0591 by N log Mn plus volt. This equation is known as the Nernst equation for an electrode potential, and this equation is very important to calculate the EMF of an unknown metal, and using this equation only the electrochemical series is framed. Coming to the applications of Nernst equation is used to calculate the EMF of an unknown metal. It's also used in physiology for finding the electric potential of a cell membrane with respect to one type of ion. It can also be linked to the acid dissociation constant. Now this Nernst equation is also finding its applications in solubility products, potentiometric titrations and pH measurements. And already I told you that this Nernst equation, using that equation only, the electrochemical series was framed. Now this is a table which is showing the electrochemical series. The electrode potential at standard conditions like 25 degrees Celsius and 1 atmospheric pressure, and if the concentration is 1 molar, then that the electrode potential is called the standard electrode potential. That is denoted as E0. So the electrodes can be arranged in the order of increasing standard reduction potential. The electrodes are arranged in the increasing order of their standard reduction potentials, and that series is called the electrochemical series. So in this table some of the important metals electrode potentials are illustrated. The standard electrode potentials are very important because we can extract a lot of useful information from this series. The values of the standard electrode potentials from the values we can assign certain things like suppose if the standard electrode potential of an electrode is greater than 0, then those electrodes greater than 0 means then its reduced form is more stable compared to the hydrogen gas. Similarly, if the standard electrode potential is negative, then means then that reduced form of that species is more stable than hydrogen. Okay, so from this table we can see that the standard electrode potential for fluorine is the highest. That means fluorine gas has got the maximum tendency to get reduced to fluoride ions. Therefore, fluorine is the strongest oxidizing agent and fluoride ion is the weakest reducing agent. Similarly, we can see in the table, from the table, lithium has got the lowest electrode potential, indicating that lithium ion is the weakest oxidizing agent. Lithium ion is the weakest oxidizing agent, while lithium metal is having the most powerful reducing agent in an aqueous solution. So these are the information we get from the electrochemical series. Now these electrochemical cells are extensively used in determining the pH of solutions, solubility product, equilibrium constant and other thermodynamic properties, and also for potentiometric titrations. Let us now look into solving some problems related to Nernst equation. Suppose a problem is asked like this: calculate the reduction potential of Cu/Cu2 plus, which is having a concentration of 0.5 molar at 25 degrees Celsius, and the E0 value of the copper is also given, which is 0.337 volt. Now how to do this problem? The solution, we have to first take the given quantities into consideration. The given values are E0 value is given and also the concentration of copper ion is given. Now the formula for this is the Nernst equation. We have to write E is equal to E0 plus 0.0591 by N log concentration of Cu2 plus ion, and the unit is in volt. We know the value of E0, it is given here. E0 value is 0.337. The concentration of Cu2 plus ion, we already know it is given 0.5 volt. And the number N is the number of electrons which is taking place in the reaction. Okay, so the reaction can be written as Cu2 plus 2 electron gives Cu. This is the reduction reaction. Any reduction reaction will involve addition of electrons. So the ion, when it is accepting 2 electrons, it is forming the copper metal. So the number of electrons that is involved in the reaction, N is 2. Substituting the value of N as 2 and E0 value is 0.337 and Cu2 plus value is 0.5, we get like this. 0.5 is nothing but it's 1 by 2. So it becomes log 1 minus log 2, or log 1 is 0. So this becomes minus 0.0591 by 2 log 2 volt. Substituting the value of the log 2, we get the answer E is equal to 0.3281 volt, which is the reduction potential at 25 degrees Celsius. Similarly, to calculate the oxidation potential of any electrode, which is at 0.2 molar at 25 degrees Celsius, the E0 value is given and the concentration is also given. We have to calculate the oxidation potential. Now for that, the solution is, write the Nernst equation formula. E is equal to E0 minus RT by NF ln concentration of the products upon concentration of the reactant. The reaction involved the oxidation, we have to calculate the oxidation potential. So oxidation involves loss of electrons. Zinc loses 2 electrons and form zinc plus 2 plus ion. So the product is Zn2 plus, okay, product is concentration of Zn2 plus and the reactant is Zn. So substituting the value of E0 in this formula, E0 value is given as 0.763. So E is equal to 0.763 minus, already the calculated value for RT by F is 0.0591 and N is the number of electrons involved in the reaction, that is 2. So you divide it by 2 log concentration of Zn2 plus by concentration of Zn. the concentration of Zn2 plus is already given in the problem, 0.2. So by replacing it at 0.2, and zinc being a pure metal, pure solids have activity or concentration only 1. So that anything divided by 1 is the same number. So we get 0.763 minus 0.0591 by 2 log 0.2, or it is 0.763 plus 0.0591 by 2 log 5 volt, because 0.2 is 1 by 5. So it becomes log 1 minus log 5. So that minus and this minus will become plus. And by substituting the value of log 5, we get the final answer E is equal to 0.784 volt. So this is the oxidation potential of this electrode. Thank you for watching. Stay tuned to watch my next video in other topics connected to electrochemistry.